Hello, Jasper.
Hi, how's it going?
I'm good. How are you, Jack? Hello, Logan.
Well,
We are, we're going to switch rooms.
Right now?
What? Not right now.
next
Okay.
week.
But on Monday. We'll start on Monday.
Do you have the list?
No. Do you have a request for a room?
Well, I'm kind of curious to see what the other one's like.
I like the natural light.
Do you want to be with Isabel or not?
I want Izzy. I want Izzy.
I want Izzy.
Who doesn't
want Izzy.
want
I want
Isabel.
Izzy. I want Izzy.
For what?
So like half,
I want Isabel.
like half her? Or like
As I was coming to class, I could swear I heard someone from Murray say, "We were supposed to do something for class today." Who would have said that?
I don't know.
I don't know either.
Definitely a
That's
boy.
shocking.
I don't know.
I don't know, man.
It was Eric.
It was not me. Classic Eric.
It was Eric, I swear.
Eric, cut it out.
Hey, do some work. Pretty sure it wasn't me, but
Shut up, Eric.
Why isn't this Ramon?
got heated.
This room's hot.
Eric, do you have a middle name?
Yes, he does. Yes.
Oh, it's
And
so
what is
cool.
your middle name?
Tetsuo?
Hetsua?
Tetsuo?
Tetsuo.
Hetsuo. Okay.
I like that. It's cool.
And is that a family name or?
You want to change?
Yeah, I mean, it's a Japanese name, but my grandfather chose it. They choose names based upon, like, the number of characters or something.
Oh,
Or, I mean, like, that factors into it, so.
that's interesting.
Wait,
You were named by math.
Yes.
No.
That is a problem.
that explains
So we will change
think
rooms
that's-
on Monday. If you have any special requests, let me know.
Creating
Oh.
out of nothing.
If you have any
Actual
special requests.
For what?
Question.
Yes,
Give
Julius.
us the first.
If I let you know, like my entire, I feel like if I request my entire room, like I might get the opposite room.
Julius, I would never do that to you.
Okay, awesome.
I would never, ever, ever do that to you.
Yeah, you can do like reverse psychology.
This is Fraggins. The remote's not working, so I can't get Julius onto the screen.
How is the
It's cool.
remote not working? Well, first of all, Julius can move
Julius,
to
you can
beside
move.
you.
Do this and open.
Good.
Bye, Juge.
Okay, I don't like you anyway.
I mean, it's
Okay.
possible. Oh, I have to do this too.
That's so awkward for me.
Where's Trinity Prep?
I don't know. They're always like, it's Easterish there.
Everyone forgot we had class.
That's Thursday? Yeah.
No, I have faith that they're going to appear.
I bet Alex Powell is on
No.
Easter break.
But Samuel, leave it. Well,
They had like
never
a
gonna lie
3-week
about it.
spring break, I mean,
guys.
why not?
It's ridiculous.
Yeah.
We'll just do first names now.
And get back from spring break and have a day of class and then they go on Easter break.
That's right. It is.
You guys
It
are
is
so
the school. There's Coleman. Hello, Coleman. How are you?
I'm doing well.
Is it like 95 degrees in Dallas?
Yeah, so is mine.
No, it's like
I don't know.
it's like 80 here.
Actually,
Yeah.
legitimately, just not let me in.
So I heard it was really hot there though last week.
But like once I figure it out, it'll be fine.
Yeah, the first half of the week is like 95, but then it was like 50 the rest of the week.
Now, does your school get off tomorrow, Coleman?
Eric, can you log in, please? You're taking a long time.
We do
flashcards out
not.
of date.
We had it was called ISAS. It was an arts festival
Uh-huh.
last week. So for people who didn't participate, it was basically just a second spring break.
So it's like you're hanging around being arty for a week.
Well, it's only for Thursday, Friday, Saturday, but they had to set up Monday through Wednesday.
My goodness, that's quite an arts festival.
Yeah,
School
there's
is
like
closed while they
4,000.
set up
There's like
Monday,
4,000
Tuesday, Wednesday.
students who come to the school.
Oh wow, there you go. That is intense. I like that name, Irka Dirk.
Logan.
I really like that. Welcome back, everybody. I hope you had some restful times, and I certainly slept late a lot and did that sort of thing. I see that. Is Isabel really here?
Yeah, where's she?
Is she at
Are
home? Is she
you
visiting?
here?
There's only 6 people.
I know, but she's signed in. Okay, I'm going to start class today by showing you 3 videos. Okay, and we'll talk about why I'm showing you these videos in a second, but I'm going to show you these 3 videos. So
for the blue jeans ID.
Okay. I'm going to share my screen with you and show you these 3 fascinating. Actually, they're not fascinating, but they're kind of cool. One of them is, in particular, somewhat ridiculous. But I'm going to start showing these videos, and we'll see what happens next. Okay. Here we go. Here's the first. It's on the glories of magnetism.
Sometimes we'll see a science teacher playing with a magnet, and occasionally they'll cover it with a piece of paper, then sprinkle filings. This produces a pretty pattern. They often exclaim, "Look, the magnetic field lines." But what are these magnetic field lines? Simply put, they're an idea visualized. Basically, they are guides to tell us in what direction a compass will point. And this helps scientists predict how things will interact with magnets. In this episode, we'll deal only with lines outside of a bar magnet. Later on, we'll tackle more subtle scenarios. However, for this case, it's quite simple. Here are the rules for drawing magnetic field lines. First, field lines start on a magnet's north pole and end on a south pole. They don't cross. Remember, they tell us the direction a compass points, and they can't very well point in more than one direction. Consequently, you can think of the lines as repelling each other. How tightly packed the lines are tells us about the strength of the magnetic push or pull in that area. The more tightly packed, the stronger the force. The lines sort of act like big elastic bands, pulling their 2 ends together while repelling other lines. We can see how this behavior requires like poles to repel and opposites to attract.
Okay. Fascinating video 1. Okay. Second video. This is like a model of a planetary system. Okay. So you have a large mass being circled, being orbited by a much smaller mass.
The jam.
Okay, not much of a video.
Some pretty epic music.
Yes, pretty epic music. And then there's an ad. Okay, stop that. Okay, next. Whoops, sorry. This is a hurricane. Okay, here's the last one.
We are watching a simulation of Hurricane Isabel created from actual data gathered during the storm. Here we are seeing a continuous loop animation through the 48 one-hour time steps in which a set of vector glyphs representing wind velocity vectors is presented at each time step. The glyphs are colored based on a separate scalar field, in this case the pressure caused by the partially simulated hurricane.
Okay, do you understand what there are 3 things here. Why did I pick these 3 things to talk about or to show you these videos? Yes, anyone? Yeah, Jasper?
Well, because they're all represented by vector fields, I believe.
Okay, so they're vector fields, and they're actually 3 of the most sort of famous vector fields. So one of them was a gravitational field, okay. One of them was a magnetic field, and one was wind, for example. And what's a vector field, Jasper?
It's like a grid that's made up of vectors that are, because each of them have this magnitude and direction, and like at each point there's a different vector representing kind of like the motion of the object if it were at that point at some specific time.
Okay, so let's watch this. Let's watch the wind one again. So say that again. What is this showing us? What's going on? What's it showing us? Jasper, the red things are what?
Well, so that's the like kind of the airflow, I believe, or yeah.
Right, it's
I think
wind or something like that.
Wind.
And I don't know if you can't probably tell it from looking at this, but it has like a component. It has two components. Some is vertical, and so let's just watch it again and see what happens.
Wait, how's the like? Can you guys
Wait a
see
second.
everybody?
Isabel created from actual data gathered during the storm. Here we are seeing a continuous loop animation through the 48 one-hour time steps in which a set of vector glyphs representing wind velocity vectors is presented at each time step. The glyphs are colored based on a separate scalar field.
Okay, why are the lines in the hurricane so long?
The wind is very strong.
Yeah, and why? And that's how. So talk more about that. So Logan said because the wind is really strong. So
the magnitude of a vector is represented by its length. So it makes sense that like the closer you are to the center or to the epicenter, I forgot the terminology, but
The eye.
The eye, yeah. The stronger the wind would be. So.
right. So those things are pretty big. I mean, the length of that tells you something about like how strong the wind is blowing, right? So the wind is blowing really strong in that hurricane part. I thought it was appropriate, of course, that it was a Hurricane Isabel, but you know, what can I say? Okay, so welcome Trinity Prep. What's going on?
Hi.
Can you hear us?
Yeah,
Can you see all of us?
I can see all of you.
Okay,
All right.
we're connected through Heve's laptop because for some reason BlueJeans isn't letting us connect.
Oh my gosh, I'm so sorry to hear that. Okay, so in your own time, I mean, if you want to, you can look at if you just do like if you look at anything that says, you know, here's you just look up vector fields, you can see a lot of very interesting examples of vector fields. I actually chose those three for a particular reason because they're the most famous kinds of vector fields that we, think about. You can think about water flow, very similar, okay? In a while, we'll talk about these gravity and magnetic fields. Those are particularly important because they are what are called conservative vector fields, which we'll talk about what makes a conservative vector field. I think the guy who was talking about the magnetic fields, he pointed out the lines don't cross. Why would that be? If it's a vector field, why wouldn't the lines ever cross? Yeah, Charles?
Well, I would guess because, well, if they crossed, then there would be a point where you would get two vectors, and then it wouldn't be a function.
Well, or there would be some major, I mean, at that
That'd be an
point, I don't know,
issue,
yeah.
yeah.
I mean, that would not happen physically. I mean, that would not happen in real space and time. I can't imagine. Even like an eddy or something that's really chaotic in terms of wind, you're only going to have one vector at one point in space. Now, none of these that we looked at, we'll look at some later. I mean, this can be in three-dimensional space, but still, you won't have vectors crossing each other like this, ever. Yeah, you have a question, Max?
Yeah. I feel like it makes sense to me in like the field lines that he was describing for the magnetic field would never cross. But I think like in the hurricane example, some of the yellow vectors were crossing just because their magnitudes are so big, and so like sometimes crossing doesn't mean that there's like a discontinuity or something. It's just
right.
that.
I think it depends on the scale at which you're looking at stuff. I think in the most micro scale, you're not going to have vectors crossing over each other. Yeah. You're going to have one vector at each point in space that is a singular vector. Yeah. So it's true that if you're looking at something, like if I were looking at maybe all the wind currents in a big room that had a wind tunnel, then I might have issues, and if I described it with one, image. And so like the thing you're looking at, it looks like there are lots of vectors competing with each other, but there's only, at each point, there's only one vector. Yeah. Logan.
What would it mean in a magnetic field for there to be, like, I get it. So like wind can't be blowing in two directions at once.
Yeah.
But for a magnetic field, what would a crossing of vectors mean physically?
Yeah. Well, you might introduce another magnet to the system or something like that.
So in
But
that
then,
case,
but then the vectors add.
it's just
yeah.
the result of the two.
Well, I think it depends if you were using the same end of the magnet. I'm not sure. I don't know.
I think if you add a point charge, you just
Yeah.
add the fields from the point charges if they were alone.
Yeah.
'Cause you can superimpose the two.
By the way, magnets are interesting because the Earth is a big magnet, and I think you all know that, right? That's why compasses work, and some people, there's a lot of belief that that's one of the requirements for life on a planet to exist is for there to be a magnetic field. So that's we know that we have a metal core, and as the Earth spins, it creates this magnetic field. So that does things like helps geese go north for the winter and stuff like that. But it also apparently encourages life. Okay, so those are some visualizations of vector fields. If you ever want to, do these on your calculator, you can do them on a calculator. There's a downloadable program for a TI-89. And one of the reasons that you might want to do that is because I will ask you to construct vector fields at some points. Okay? And there are a couple ways you can do it.
Like on a test when we only have the calculator?
Or on a homework assignment, you might have to do it. But they're not hard to do. But I use this program a lot. This is a vector field. This actually just creates a vector field. And again, I'm going to stop. I'm going to show you my screen so that you can see what it looks like. And it's a very beautiful program, actually. It is right here. And this is a vector field of xi plus yj. Okay, so I'd love someone to explain to me how this thing was created. Sam, do you want to try? Like if you were drawing it by hand, how would you do it?
I guess I would just, use few points and then see what the slope would be at those points.
Yeah. So it's very similar to Isabel mentioned. What did you mention, Isabel?
Slope fields.
Slope fields. Tell me how you did slope fields. Do you remember how you did that?
You would calculate the slope. You would plug in the point into the formula and calculate the slope, and then you would just draw the little line.
Right. So how is this different, Isabel?
Well, this isn't just slope, it's a vector.
Excellent. So at the point 1, 1, what would you do?
Well, plug in the values and calculate the vector.
Yeah. And then you draw a vector 1, 1. Okay, its magnitude would be the magnitude of the vector 1, 1. Okay. And it's could someone explain to me why this particular slope field looks this way? Coleman, want to try?
Why it looks that way, or the properties of it? Because as you're getting further away from the center, the magnitude of the vectors are increasing.
Right.
But the direction is always opposite the center.
And why is that? That's true. I hadn't thought about that. And why is that true?
I'm not sure.
It's obviously, so Max, you have an idea?
Yeah, so I think what this is trying to describe when it says xi plus yj is, and I almost don't believe that this is what it looks like because
I'll
tell you why. Because I assume I and J are talking about the unit vectors I and J, and so what it's saying is for any point xy, you're gonna get the vector x times the unit vector I plus y times the unit vector j, and what that means to me is that for any point, the vector that you're asking for is the vector from the origin to that point.
That's interesting. Okay.
At that point. And
Okay,
so,
okay, that's one thing about constructing these that is not, so I'm going to construct it by going to the point and start my vector there. So you're not actually drawing all your vectors from
I understand that. But what I'm saying is like, so let's say like at the first, I wish I could point at it, like the first box, the top right part of the first box.
Right here?
Let's say that's 1, 1, right? So the vector would be the same vector from the origin to the point 1, 1, but with its tail end at the point 1, 1.
Yeah, I think part of what's hard about this is the scale.
Yeah.
I mean, if I change the scale of this, I think, like, I don't actually know. I've never tried to mess with this thing down here, the scale part. But if I change that, I think it might be more what you're talking about. I think that this is supposed to be a vector of length, root 2. And out here, it's supposed to be, notice the scale is from 0 to 10.
Multiplying all of them by 0.1.
Yeah.
Okay.
So it's making it much smaller so that it can fit on this screen. Okay?
Yeah.
So you can change this. Oh, look at that! You change the scale, and it looks terrible. Okay, so this is a kind of an interesting thing. So you could think about, like, what might this represent? Can someone give me an idea of what this might physically represent?
Oh.
Yeah.
Well, if you had a positive charge right at the center, then this would be the force field for.
Okay, you could have a positive, point charge.
Mm-hmm.
Okay, and this would give you something about the maybe electric field. Okay?
Yeah, it wouldn't be this exact scaling. It would have a square term.
Okay, but this actually, so if you think about this, you have some force in the middle that's pushing stuff away from it. So it could be a north pole, of a magnet or something like that. So there are three fields that we love: the electric field, the magnetic field, and the gravitational field. And one of the reasons we love them is because they have this property of being a conservative field. Logan.
So that makes sense why like a north pole or like a charge would want to push things away. But why would the force experience be like greater as you go farther away?
Yeah, it's not. Yeah. It wouldn't be for I think either an electric field or a magnetic field. Okay. I'm just trying to think about something that would make this pattern of stuff going around. So it's a good question. I don't know what physically would create this. Something that's
maybe like a hill. That was really.
I don't know. This is a very, but this program, I encourage you to use it. If I ask you to draw a vector field, it's going to be much better for you to do this kind of thing than to do it by hand. Coleman, you had a question, or?
That was my question.
Yeah. So okay. So those, I want you to make sure that you use those tools if you would like to use those tools. Those are good tools to use. Okay, so let's look at a definition of a vector field. So sorry. Okay, so you should have this definition somewhere in your mind. There are these two definitions that we're going to talk about today. So one is a vector field. And it's a vector field, and notice it's a vector field. It's got F with a little arrow, which means it's a vector, right? That means that it's a vector. And it's a rule which assigns a point xy a vector f of xy. So giving a vector field is the same as giving a vector function like that. Okay? Now, important things, it's a vector, and you typically have an equation, an expression, a function that describes how the x is behaving and how the y is behaving. Okay? So that's what a vector field is. And the second thing, so vector fields are not going to feel like, they're going to feel very similar. And in fact, I'm glad Isabel mentioned slope fields, because we also talk about this idea of flow, which, if you imagine the vector field as a drawing of flowing water, however, like if you had a bottle that you dropped on that vector field, what would the path of the bottle be? That's what we call flow, okay? And I mention that because, in slope fields, right, do you remember how you would draw the little, kind of ghostly, function that you could see? But this is, the image that you should have here is like you're dropping a leaf on this flowing water. How would the leaf behave? Okay, so those are called flow lines, how the leaf would behave. And obviously it would behave differently if you dropped it at different places, right? That makes sense, I think. Okay, those good? So those are the two definitions. We'll talk about vector fields for the rest of the year. Flow we'll talk about for a moment because it's an interesting idea and it's very easy to deal with. Okay, now I want to let's try this. So let's play a little game here. Here are two vector fields. Okay, try to come up with a formula for the vector fields. And, there are a zillion answers for this. So let me explain, if it's a little hard to see what this looks like. So on the one on the left, you have all the vectors are pointing to the right, on the right of the y-axis, and to the left and the left of the right y-axis. And they increase in magnitude as they go from right to left and from left to right. Okay? Secondly, the next one it's like the one that we just looked at, but it's the opposite. Everything is pointing inwards, but it's getting bigger as we go forward. Okay? So everyone think about this. I want to hear as many different possible answers as I can hear. Sam, give us a response.
For the first one, Samia's computer isn't working.
Yeah,
so
I raised my hand as Sam.
Okay, so Samia.
Okay. The first one, it's not very creative, but it's just xi.
Mm-hmm. And then you would want to say xi would be fine. So you could have any kind of multiplier by xi. So a constant times xi. Okay, great. Thank you, Samia. Did anyone else have a good one for the first one? Yeah, Charles?
The cube root of x times I.
So the cube root of x times I, would that work? I think anything, I don't know. This is what I'm curious about. Would anything that's just a function of I, would that work?
I think anything continuously increasing.
I don't,
Yeah, anything that's continuously increasing in terms of I and maintains the sign of its input would work.
Okay, so I think that works. Okay. Irkaduk Matsu Photo.
That's me.
Okay.
Am I supposed to? I was gonna do the other one.
That's okay.
The next one. So negative xi minus yj.
Okay, explain why that you think that works.
Well, I guess in one way, it's the opposite of the one where everything was pointing outwards. So it makes sense that everything was going out before, so it makes sense that everything's going in now.
Okay, and would the vector lengths get bigger as you go out towards the edges of the graph?
Yes.
Yes, I think so. And would they all be pointing towards the center?
Yes.
So, and then you'd have some positive and some negative. Okay, that's good. Okay, Isabel, do you have a different idea?
I have a question about that. Because that's what I wrote too, but then I was thinking, how along the axes do you make, like, if you have a vector 0, 4, like, how do you make sure that it's going to be pointing inwards and not outwards?
So
or 0, negative 4.
Isn't the expression negative x, negative y?
Right, but there's no such thing as negative 0.
No. So your point was 0, 4?
Sure.
Is that what you're asking about?
Or no. 0, 0, negative 4. It's like it's.
It puts straight up.
So at 0, negative 4, what would I do to graph that point?
All right, never mind.
So I would go to y equals, so it would be 4, right? And I would go.
Never mind.
Yeah, I think it works okay, doesn't it?
Yeah.
Yeah, it's headed in the correct direction. Everything. Okay. Good question. Coleman, do you have another idea for any of these, or?
Coleman. That's funny.
It was the same one.
Okay, cool. Okay, I'd love someone to try to draw this. Who's willing to try?
Like on the screen?
On the screen. Okay, let's see. Akshay, you want to try? Okay, Max is volunteering. So Akshay, why don't you try the left one and Max try the right one? This is going to be, we'll see what this is like.
Yeah, yo, man.
And all of you should try, so what would, like 2i plus 3j, that's a really interesting one. What can you say about that one, Julius?
2i plus 3j?
Yeah.
I want to say, again, everything is pointing away from the center.
Okay. Is that true?
What?
I think so, yeah.
Everything is pointing away from the center?
Mm-hmm.
Huh. Really?
I don't agree with that.
Oh, wait. Oh,
why don't you agree with that, Isabel?
Because that would mean that at every point the slope or the vector is 2, 3.
Yeah.
So, yeah. I think I might be with you. I saw someone draw something and then it just... Oh. Beautiful. Love that.
Is that an axis?
It was. I think it was. I think it was an axis, but then it went away.
Wait. Am I drawing the axes first?
Okay. Cool.
Murray versus Trinity Prep. Math off.
Oh, wait, I get it.
Okay, you get it. Good. Tell me what.
What I said before was wrong.
Yeah.
Everything does have the same. It just has the same slope.
Yeah. Every vector, and they all have the same magnitude, right?
Yeah.
It's like
So it's just like a bunch of lines.
It's like a super boring vector field.
Oh yeah, that is right. Because before there was like X and a variable.
So those of you who aren't drawing it, you might try that program that I showed you, to see what they really look like, just to have a little experience with that program and fiddle around with it. Pretty, huh?
Yeah.
Oh, that's cool.
You wouldn't expect it to be like that circly, because
right.
Like it's such a simple equation.
Do I need to draw that? Oh, should I be using the arrow tool?
Here.
Oh my god. Eric, take it away.
Ermagerd.
Whoa.
Akshay.
Oh, Akshay.
Ermagerd Mercs.
Okay, hold on.
You got a round of applause for this gentleman.
Yeah, etc. Right, Akshay?
The other one is cool.
I think you need to draw the other 500.
I know. Yes. Could you draw exactly the other 1,000 ones in that?
This one is cool.
Okay, Max, tell us what you're up to.
So it's actually kind of hard to draw because I'm gonna pick a couple.
Okay, so explain why you think it looks that way.
Okay, so this is just the first quadrant.
Yeah.
So since it's in the first quadrant, all the y's are going to be positive, and so depending on where it is, what y value it has, it's going to go up further. So that's represented by where can I arrow?
This thing next, yeah, right next to it.
Okay. Yeah.
Click on it and then, yeah.
Oh.
You have to turn off your draw before you do that.
Oh.
Ah! So sorry. I guess you can't.
Maybe don't turn off the draw.
Yeah.
Okay. So the y keeps getting bigger, and then the x is negative, and so the further it goes in the positive x direction, the larger it will be. going in pointing to the left.
Okay,
And
so now I'm curious, Logan, do you like Max's drawing?
I do.
You do. Okay. How do you like it? How do you like it, Coleman?
I can't see it. Am I supposed to be able to see this?
You can't see it.
Well, I can see it on the board.
You can't see it on your computer. That's interesting. I wonder, are you signed in?
Yeah.
No, I'm
Maybe
sorry.
I'm not.
It's pretty looking. It actually, I especially like the etc. So Charles, what is your?
So I have a are we critiquing the right one?
Yeah.
Yeah. So I have a slight qualm about the right one because it seems like if you look along any row or any column, if you look along this kind of first column, the x isn't changing, but the and the y coordinate is changing, but the j coordinate is getting bigger, and the I coordinate is staying the same, which is kind of opposite of what. Because the j component is determined by the magnitude of x, and the I component is determined by the magnitude of y.
Touche.
So what do you think?
Okay.
I mean, it's not super easy to do. I mean, it is super easy to do. Who is that? Who is that just wandered in?
My friend, sorry, I've got people coming here all the time. I'm really cool.
Well, let's look at here's what they really look like. Just FYI, here's what the two things really look like.
Whoa.
Okay, so Akshay, you didn't draw nearly enough. You didn't draw nearly enough of those 2i plus 3j, but you kind of had the idea. But yours looks really different.
Mine?
Yeah.
That's kind of weird.
So tell me why. Tell me what you did. What happened?
Okay, so Charles is exactly right.
Surprise.
That never happened.
So I am shocked personally.
Yeah, I'm surprised.
No, you're not.
I was drawing the vector field x comma negative y, or like vector x and then negative y, instead of y negative x.
Yeah.
And so
can I show you the other
in
picture?
In reality, all of these should be going.
So wait, let's see. Can you explain why it looks that way?
Yes. So on the x-axis, everything's dependent upon y.
Why does it have this funny circular motion? Alex, do you want to try? What's with the circular motion thing happening here?
I'm really not sure.
Okay.
I'm trying to figure it out.
Yeah, well, so take some points, Alex. Just truly pick some points and see if you can explain why it looks that way. Jasper, do you want to try?
Yeah, well, when x is really big, the y component is going to be really large in the negative direction. And when x is really small, I mean, negative small, then the y
negative
component
small.
is sorry, yeah, like -8. Then the y component is going to be really big in the positive directions. Then you kind of get going down this way, going this way, and in the when y is really big or y is really negative. Then then the x component, I mean the I component, which is going to go either this way when I is really positive, or this way when I is really negative. So you get kind of the swirl going all around, but just at different magnitudes depending on how big each of the components are.
Okay, Eric, why is it so tiny around the origin?
So because there's a 1-to-1 relationship or ratio between the x and y, but they're just flipped. So like Jasper was saying, you're going to get the opposite. Like when x is large, you're going to get a large j component, and instead of what we were used to in the other one, which was looking at x and I together and y and j together, it's just flipped, but the magnitudes stay the same.
Okay, Alex, how does that feel? Does that make sense?
Yes.
Yeah, I mean, it's actually not. It is different from drawing slope fields, and we're pretty comfortable with drawing slope fields. But the notion here is that you take a set of points, you draw a vector, you put it into your formula, and you draw the vector subsequently that you get out. So you're really truly picking points like 3, 3, 3, and so that vector at the point 3, 3, I'm going to go over to that point and draw the vector 3, -3. Okay, and so when I go up here, that's why I get a vector that looks like this at 3, -3. Okay, that's why I get that at x equals 3, y equals 3. Okay, I generated these using that program, and I really encourage you to use those if you ever need to draw them, because it's a very nice program. But if you want to do it on your calculator, you can do them too, and it's a kind of a useful kind of thing to do. Okay, so let's see. Here's a kind of a more a question that's a more qualitative question. Do you understand what these things mean? So again, it's a little hard to see, so let me just describe what we're looking at. In the graphs below 1, everything is pointing in towards the origin, okay? And it's stronger, the vectors are longer at the origin than they are on the outside. Everyone see that? That's for graph 1. For graph 2, everything is pointing towards the center. However, the vectors are getting smaller as they go towards the center. Okay, for graph 3, everything is pointing outwards and they're getting bigger. The vectors are getting bigger as we go outwards. And in graph 4, same way, except for the vectors are getting smaller as we go out. Yeah.
So, and I guess like an infinitesimally small particle like put in graph number 2,
yeah,
it would never technically reach the center, correct, or the origin.
Well, what do you when we say it, what is the antecedent of it?
Like the particle, because I'm trying to.
Oh no, a particle could.
It would reach.
But would it come to rest at the center?
Yeah, but it would hang out there. It would go. So think about like a bottle. Like if I drop that's water, it's going like this.
But eventually, there's going to be. Okay.
There's something happening at the origin. I don't know. It may have a sink or there's this and I can't remember if we'll talk about this later. But there are these notions of sinks, and it might be a gravity sink or something like that. But like if you dropped a leaf on that, it would definitely go to the origin and stop.
Okay.
But unless there's some force damping it, I don't think it will. By conservation of energy.
Well, I mean, I'm saying you're saying it. What do you think it would do?
It would go to the bottom, but it would have kinetic energy at that point, which would be enough.
But I think I think the force. I don't know. That's a good question.
If there was something like friction that dampens its motion, then it would eventually.
I don't know.
Stop.
Okay, so let's read this. Each vector field shown represents a force on a particle at different points in space as a result of another particle at the origin. Match up the vector fields with the descriptions. Okay, so let's see. A repulsive force whose magnitude decreases as distance increases, such as between electric charges of the same sign. Sam, you have an idea?
Wait, you mean Sam or the person whose hand is raised?
Sam!
The real Sam. Number one cup.
So it's repulsive. So which way should the arrows be pointing since it's repulsive?
1 and 4.
Okay, so let's see. And its magnitude decreases as distance increases. So I like 4. Do you like 4? Do we all like 4 for 1?
Yeah.
Okay, good. Okay, a repulsive force whose magnitude increases as distance increases. Jack, what about that one?
3.
3, okay, because it's being repulsed. Okay. An attractive force whose magnitude decreases as distance increases, such as gravity. Logan, which is that?
Decreases as distance. It would be number 1.
That's right. So, in fact, that's one of the things that is really interesting about gravity, and what's important about it, and what Einstein discovered is that gravity creates these, actually curved space around it, so that it's like you can almost think about like a massive body, if you on a sheet, and particles going towards it are pulled in towards it. Like they fall towards it. So, that was proven in his lifetime that happened. So that's number 1, I think. And number 4 then I think is number 2. Okay? So gravity is actually looks like number 1 if at the center you have the sun. Okay, or some massive body. Okay? Cool. Oh yeah, let's see. Now, here's something totally different. Level curves and gradient fields. Now, gradients, why are gradient fields and level curves? Why are you even talking about this anymore? What are gradient fields? I don't even remember what the gradient is. Holy crap. What's a gradient? It's a vector, right? It's a vector. So a gradient field is like a vector field. So how do I know how to match these level curves? What do we remember about the gradient? Oh my gosh, I remember nothing about the gradient. Jasper, do you remember anything about the gradient?
I remember that it's perpendicular to contour lines, and it's the direction of maximum increase is the direction where the gradient points.
Okay. Cool. So it's perpendicular. Okay, so let's see. I'm going to give everyone a moment to think about this. Let's see if you can match these, the graphs up in the left with those gradient fields. And let me describe the gradient fields. In the first one, everything is pointing out diagonally. In the second one, everything is pointing, all the vectors are the same length, and they're all pointing to the lower left. In the third, they're all the same length, but they're pointing to the upper right. And in the fourth, they're all pointing to the center of a diagonal. So everyone look at those and see if you can match which goes with which.
Oh, yeah. You guys are distracting me.
So Jasper's point explains why they all are pointing in the direction that they are, because they're all perpendicular to these lines. All the vectors are perpendicular to these lines. Who is Samya Frowny Face?
It's me, but it's Sam.
Oh, that was
computer.
Eric Matsumoto.
There you go. It's Eric Matsumoto. Eric, why are you taking over Samya's name?
Wait.
I just like it so much.
I know, it's a pretty amazing.
Frowny Face is Sam's computer. That's why it's
I love her.
I really like Urkadirk. It sounds very Assyrian. You know, like
Eric's
Babylonian.
Eric's nickname. Urkadirk. Who did that first? But I think it was probably Logan. It must have been Logan because I would never say something so dumb.
I met a girl named
I've never seen that. I love the.
Wait, is that Brody or is that Brody?
Oh, Brody? Did someone do Brody?
What? That's Brody or Brody? I think it's Brody.
It's Brody.
Is this true about you, Eric? I didn't know that.
Yes, it's all true.
What?
It's true.
Eric's just a lax bro, you know.
I know. I knew that, but
Yeah.
You
know.
put up 16. Dude, you know we're in class chill, man.
Eric, would you prefer that I called you Brody?
Ooh, Akshay salty.
Whatever
yes,
works.
Yes,
Or
do it.
or Bro Sidon.
Bro Sidon, king of the Broshan.
Okay.
Charles, can you not play my game better than me?
Inside jokes, SMH.
Urkadirk. I'm calling on Urkadirk. Do you have any belief? Do you have any of these that you know that you think are right?
As in me or Julius?
I don't know who Urkadirk is. I think it's Julius.
Oh, me. Okay, well, I want to say that A and D are the ones with 0 in the middle.
Okay, A and D are the ones. And why do you think that?
Because there's no slope at those points.
Huh.
Or the slope.
Interesting.
Okay, well. That word strikes fear in my heart. So I don't really know where to go from that.
Continue. Maybe that could be right. So say more.
Okay, got more. so rough. Okay, so I want to say that A is 1.
Okay, and tell me why.
Why?
Does the length of the vector tell you anything?
So yes.
Yes. Doesn't it tell me?
Why, Alex Johnson? Why does it tell you something?
Oh, yes.
Because like as the values increase from like, so if you're looking above per se 0 in the level curves of 1, it goes from like 1 to 3 as you go like this direction, and they're increasing in magnitude as you go, or maybe they're not. I actually can't tell. Maybe they are.
Well, so it is relevant. By the way, it is relevant
like
that
they
the
are.
lines in 3 and 4 are closer together, right? That is important to figuring out which goes with which.
I don't think you really need that, do you?
Well, it is relevant, right? Because remember the. So Isabel, what did you have? You have some ideas?
They move in different directions.
Yes.
Yes.
I said that. Should I just say just pick one?
Give us
or
one.
all?
Yeah, pick one.
I said 4 was A.
4 was A. That's a pretty different answer than what I just heard. Why do you think 4 is A?
Okay, so you see that the level curves are getting closer to each other, so then the vectors must be shrinking. So in A, the vectors are shrinking as you go further away. And it's also going, like the center line, -1, as you go away from it, the values are increasing. So I said that then the vectors would point towards the direction of increase.
That is true. That's a fact about the gradient that Isabel remembers. So I actually like A is 4. So I think that's a correct answer. Okay, A is 4. Okay?
Wait, Izzy,
Yes.
can you explain that again? I don't think I followed that.
Okay, so my first thing is that the level curves are getting closer together, meaning like the vectors need to be shrinking because the distance between each curve is shrinking. You don't need to like change as much to get to the next curve. And then my second thing is that, okay, does that mean it's like 3 or 4 for A? And because the like -1, like as you go away from -1, you're increasing. I said the vectors will point in the direction of increase, not the direction of decrease.
Okay. Yeah.
And that's a fact about the vector that you may not remember, but the gradient, rather. The gradient always points in the direction of increase. Okay? Okay, great. So I think A is 4. I agree with you. Let's see. Samya Frowny Face.
Okay, I think 2 is B because
I agree. 2 is B. Tell me why.
Because just like Izzy just said, that it points in the direction of the increase, and since it's going from -3 all the way to +3, then the gradient's going to be pointing in the direction the steep part. It's going to be.
And they're all the same size. Why are they all the same size?
Because all the lines are evenly spaced.
Yeah, excellent. Okay, perfect. Okay, Alex Johnson, go next.
Sorry, did he just do 3D? Is that what he just did?
No, she did 2B.
Oh, okay. Then I'll do 3D.
Okay.
Because basically, with the similar logic for 4A,
yeah.
It's just like it's basically it in reverse, which is what the gradient field is as well. So I just like a pretty natural inference to make.
So it's pointing. The vectors are pointing towards that line because the increase is going towards that line of 1. And that leaves us with C, which is 1. Jasper, explains why C is 1.
Well, C is 1 because, as you can see in the contour lines in the left graph, you have they're all increasing, but at fixed increments. The contour lines are spaced evenly, so that means that the gradient is going to be the same magnitude, and it's going the same direction because it's always increasing at the same magnitude.
Great. Fantastic. Okay, I actually want to just look at. Can someone tell me what's wrong with the second? These are 2 false statements. Okay, one of them says a plot of the vector field g of xy equals f of 2x 2y tz can be obtained from a plot of the vector field f of x, y, z by doubling the lengths of all the arrows. And the second one says a vector field f is defined by the formula f equals x squared minus yz. There's some problems. Both of these are false statements. So I'd love to hear why they're false statements. Jack, do you have any idea about either one of those, about why they're false?
A little bit.
Sounds like a name.
Hint, number 2 is easy.
Is that a hint?
Are you saying I'm dumb?
No. I'm just saying number 2 is easy.
He's saying you're dumb, Jack.
I mean, the second one, that's just like not how you notate a vector, is it?
Yeah, it's not a vector. That's the problem, right? It can't be that can't be a vector field because it's not a vector.
It's a scalar field.
It's a scalar, yes. I don't even know what a scalar field would be, but anyway, yeah. Okay, so you want to try number 1, Max?
Yeah.
Okay, Max, let's try number 1.
I think what would be a correct statement, or actually, the bold means vector, right?
Yeah. Mm-hmm.
Okay. So I think what would be a correct statement would be a plot of the vector field g of xyz equals 2 times f of xyz can be obtained by the plot of the vector field f of xyz by doubling the lengths. I think that would be true. The reason why I think the current thing is true is you're doubling the input, not the output. And so let's say you had a function x squared, and you let's say you input an x 1, and so x squared 1 squared would equal 1. But if you said 2 times 1, 2 times 1 is 2, and 2 squared is equal to 4, and 4 is not double what 1 is.
Right. So there's the doubling doesn't work.
The doubling doesn't always work.
So sorry. Yeah. And that number 2 is just not even a vector. Stupid thing. Okay. Flow I mentioned, which is this really easy idea. I think, flow, like you drop a bottle on the water, where does it go? So it's pretty clear looking at this lovely vector field how a leaf or a piece of paper would go along, if this were water or a piece, so it's pretty easy to do that. But let's look at this last little thing just to end class today. So here there are vector fields and then there are flow lines. Okay, so this is actually quite challenging. Okay, let's see if we can figure out one of these. So I don't show you the vector fields, but I show you the flow lines. Do you understand what I've given you here? I've given you an expression for the vector fields, and I've said this is what the flow lines look like. Okay? Everyone clear what you're given? Can someone maybe think about... it seems like a lot of people already have ideas about like which one goes with which one. So I'd love to hear some ideas. Jasper?
Well, I was kind of thinking about what we did earlier with the the circles, and so I was thinking that the negative y I plus xj could be possibly the first one.
Okay, and tell me why.
Well, because in this situation, it was the case that when the x value was really big, the y component was really large, and when the y value was really big, the x component was large but in a negative way. And so when I'm looking at 1, it seems like when you have like an x is like when x is like 5 or something, then the y component is going to be really big, and when y is 0 in that instance, then the x component is going to be small. So it's going to get like circle thing going again.
Yeah, and which direction do you think it's going, clockwise or counterclockwise?
I think it's going. Let's see, x. I think it's going. I think it's going clockwise.
I mean, I think it's an interesting question, right? Which way is it going? So that's something I'm going to pause right there. We'll start class with this question first. I need to make one quick announcement. If you look at the syllabus, there's a quiz listed, and it is truly a quiz. It's 4 questions, 1 page. And I think you're supposed to do that by a week from yesterday. Okay? So you can take, I don't think anyone will have time troubles on this one.
How long is it? Just for planning purposes?
I think it would take a half hour most. It's 4 questions. It's very aligned with the review sheet. So anyway, so take that by next Wednesday. Mm-hmm. And on your problem sets, I'm starting to allow you to have some more choice in the problem sets in terms of choose 2 of these problems, choose 2 of these problems. So I try to be very clear how many I want you to turn in. I will see you all on Tuesday. We're going to talk about line integrals on Monday, whatever day. And we're going to talk about line integrals that day. Okay? Have a lovely day. And Murray kids, notice I will send you a note about the room switch.
Show your request.
Yes.
I like the natural light in the other room.
Okay. Bye, all. Have a good day.
Yeah.
Happy Passover, etc.
Happy chocolate.
Or Easter.